Okay, okay, let's start. So now this is going to be a new chapter. Okay, I think some of you already started with your teachers. Yeah, reaction kinetics. Okay, so this reaction kinetics is going to be divided into two parts. Yeah, so for today we are going to do part one. Okay, and then on Thursday we are going to do part two. Yeah, so we just without wasting time, let's move on. Now in your AS, okay, we have learned that there are five factors, okay, affecting rate of reaction. Yeah, this is something that you should know, okay, by heart. Yeah, factors affecting rate of reaction. So concentration, temperature, catalyst, pressure, total surface area. So I'll just go briefly. Yeah, so for concentration, how high amount of concentration can affect the increased rate of reaction. Okay, because if you have more concentration, it means that you will have more particles. Okay, if you have more particles, it means there will be more collision. Okay, therefore we are going to have more reaction taking place. For temperature, okay, when the temperature is high, generally we are talking about a lot of heat energy. This heat energy is going to be converted into kinetic energy. So kinetic energy, the particles will start to move more, so they will collide more, okay, with each other, and then reaction can actually take place. And for catalyst, okay, catalyst is going to provide an alternative pathway, okay, with lower activation energy. So if you provide an alternative pathway with lower activation energy, what do we have? Okay, we are going to have more particles able to achieve or able to have that energy to start the reaction or to get the to form the product. Okay, so catalyst is going to be one of the factor, okay, to increase the rate of reaction. Pressure, okay, high pressure, okay, will decrease, okay, high pressure, okay, will increase the number of particles per unit volume. Okay, so it means that in one particular volume, you are going to have a lot of particles over there, so they will be able to collide more with each other. Okay, that is going to be pressure, which is high, you are going to have high rate of reaction. And total surface area. So if you are using powdered, okay, reactant, okay, compared to solid, just simply solid, the powdered reactant, okay, will react more because there will be more surface area for the reaction. Yeah, so this one, all these are the factors affecting rate of reaction, which you should know. Yeah, but for A2, yeah, we will begin, okay, with the rate of reaction definition. Now, what is going to be rate of reaction? According to the syllabus, according to your textbook, yeah, rate of reaction is going to be change in concentration, okay, divided by time taken for this change. Now, do remember, okay, rate of reaction can be also measured in other forms like volume, yeah, electrical conductivity, and so on. But since it's actually the one that is defined in your syllabus and defined in your textbook, yeah, we will focus only on this. Okay, change in concentration, okay, which should be, okay, the mole, okay, per dm cube. Okay, and the time that we will use is second. So what we will have, okay, the unit for rate of reaction is going to be mole per dm cube per second. Okay, this is going to be the unit for rate of reaction. And you can see the example given over there. One of the example, convert the following rate in units mole per dm cube per second. So what we need to do is just to change this gram, okay, of iodine, you change it into number of moles. You can see the marking key over here. You change it into number of moles, you have 1 times 10 to the power of negative 3 mole. Okay, and then it is going to be consumed in 1 hour. Okay, since it's going to be in seconds, okay, you need to change 1 hour into seconds. So 1 hour is going to be 3,600 seconds. So what you need to do to find the rate of reaction, okay, just take the number of moles, divide by 3,600 seconds, and you will have the rate of reaction based on the definition that is required in your syllabus. Okay, so this is going to be rate of reaction. So do remember from this slide, okay, what you can actually come up, rate of reaction is going to be change in concentration divided by time taken. Okay, as simple as that. Now, when we measure rate of reaction, there are two main methods, yeah, to follow a course of reaction. Okay, why we need to follow the course of reaction? Yeah, probably when we analyze, okay, we want to plot graph, and then we will do further. We are going to actually determine the rate equation. Later, we will go into that. Okay, so there are two methods. Okay, the method number one is going to be sampling. Method number two is going to be continuous. Now, I have made an extra video on this. Yeah, so it's in YouTube. Okay, you can actually go and see there. Okay, but I am simplifying this. Okay, in here. Okay, in one slide, which is going to be sampling. What is sampling? So when we do a particular, let's say there is going to be a particular reaction. Okay, we take a small sample, okay, of the reactant, of the product, whatever that you want. Yeah, you take at various times. Okay, t equals to 0, t equals to 20, t equals to 40. You take, okay, at various times. And what we need to do, because the reaction, like say for example A plus B to give you C plus D. Okay, the moment you take the sample, okay, the reaction is ongoing. Okay, so we need to do something to stop that reaction, because I still want to do analysis over here. So what you need to do, you need to quench the reaction, or quenching must be done. Okay, what is quenching? Okay, you need to stop or slow down the reaction. How can it be achieved? Yeah, based on rate of reaction. Okay, there are a few ways. Okay, the one that is mentioned in your textbook, you cool them with sample of ice. Okay, you decrease the temperature. The moment you decrease the temperature, okay, the reaction will be slowed down. Okay, and then you can carry out your chemical analysis. What kind of chemical analysis that we are talking about? Since the rate equals to, okay, change in concentration divided by time, we want to find concentration. So when we want to find concentration, okay, the type of chemical analysis that we will be doing is going to be, we use titration method. Okay, neutralization. Okay, then we do calculation and we find out, okay, the number of moles. We can find out the concentration, and then we can actually plot the graph, and then we can do further analysis. So these are going to be in simplified way. Okay, what is sampling? You take small sample at different time, you quench the reaction, and then you carry out chemical analysis. Yeah, so that is going to be for sampling. Okay, but there is going to be another method which is going to be continuous. Now for continuous, okay, you see here one important point over here: no need to carry out chemical analysis. Why? Okay, because we are going to monitor physical properties. Yeah, physical properties such as what? Okay, we can monitor color changes. We can monitor electrical conductivity. We can monitor changes in volume, changes in pressure. So we can actually come up with all these devices. Yeah, if you are measuring intensity of color, you can use colorimetry. Yeah, colorimetry is different than calorimetry. Yeah, so colorimetry is going to be to measure the color intensity. You can measure electrical conductivity, okay, using conductivity meter. Okay, let's say there is going to be ions being formed, free moving ions. Okay, they can conduct electricity. You can measure increase in electrical conductivity. We can also like set certain equations. Okay, they will give you gas. Okay, so the increase in volume or increase in pressure, you can measure. Okay, like for example, if you want to measure the changes in volume, I think in your textbook they mention about this dilatometer. Okay, you can also use that. Okay, you can use gas syringe. Okay, changes in volume. Okay, a lot of things that you can use. Okay, but what is important? You are going to do continuously over a period of time. You do not need to take small sample and then quench the reaction and carry out chemical analysis. No need. We are going to monitor them continuously. Yeah, no need to take small samples. It's going to be throughout. So you can actually do this continuous method depending, okay, depending on the reaction itself. Okay, when do we use sampling? When do we use continuous? You have to decide. Yeah, that is very important. So here, okay, if you look at this checkpoint number 1, okay, they are asking you, yeah, suggest a possible suitable method okay, following progress of each of these reaction. So if I want to follow this progress of these reactions, what do I need to do? First, look at the equation. You can see here, the moment I see this equation, I do see ions. Okay, and I don't see any ions. So first of all, maybe I can think about, okay, electrical conductivity, because electrical conductivity is going to decrease. Ions is going to be used up. Okay, so I can use, okay, electrical conductivity. If let's say I don't want to use electrical conductivity, is there any other way that I can use? Of course can. You can see I2, okay, I2 is going to be brown in color, okay, and I minus is going to be colorless. You see the intensity of the brown color is going to be increasing. Okay, you can also use colorimetry over here. Yeah, here you can see here. Okay, you can measure the color. Yeah, so colorimetry. And last one, okay, you can actually do titration with sodium thiosulfate. Okay, this is going to be, if you have I minus, I2, I think you can do the titration over there. Okay, but okay, in the end, okay, if you summarize here, okay, if you measure electrical conductivity and color, okay, please remember and take note, this is going to be physical property. So this is going to be continuous method. Okay, and this is going to be titration, sampling. Yeah, sampling method. So do remember, if they ask you to go and explain more, you should be able to explain more. Yeah, so you can see the second part over here. Okay, this one done. Okay, if you look at the second example, okay, I have, okay, forming this methanoic acid. Yeah, forming methanoic acid, and I don't have, okay, the moment I look, yeah, I don't have any free moving ion. So maybe I don't think about electrical conductivity. Okay, the moment I look over there is no gas. Yeah, I no need to think about volume of the gas, okay, or pressure. No need to think about that. The only thing that I can think about this methanoic acid can react with base. So you can just use the titration method. Yeah. So that is going to be what we call as, you do the titration using the a base, sodium hydroxide, you react and find out the concentration of methanoic acid that is being formed. You keep track of that. Okay, the concentration is going to be more and more. Okay, so you can actually find out the concentration of methanoic acid. So this is going to be sampling. This is going to be sampling. So how to do this sampling? I already told you. Yeah, you take small sample. Okay, you quench the reaction. Okay, and then you do the chemical analysis. In this case, you do titration. Yeah, you find out. You put the sodium hydroxide. You put acid base indicator, and you find out. Yeah, what is going to be the concentration you calculate. Okay, that is can be done. So here, okay, number 3, the first moment that you see the product is going to be gas, yeah, I will suggest, okay, no need to think, okay, no need to think about, okay, anything else. You can just measure the volume of the gas produced. Yeah. Now Shannon was asking, okay, how? I'll just read the question over here. How does sodium thiosulfate help us to perform chemical analysis? This one, Shannon, please go and find out. Sodium thiosulfate will react with what? Will it react with iodide or will it react with I2? You can come up with the equation. And once you do that, okay, you are going to be able to find out what is going to be the concentration of the iodide or I2. Yeah, you can go and find out. Okay, this is not acid-base titration. Yeah, but it is titration. Yeah. Now, for 4, okay, BrO3, you can see here, okay, there is going to be Br2, but aqueous, okay, do remember, bromine in aqueous form, okay, they are going to be brown in color, yeah. So the moment you see Br2, the moment you can identify there is going to be color that is going to be given, straight away, okay, you can use colorimetry, yeah, straight away you can use colorimetry. But here I think the answer is not complete. Yeah, if you want to use colorimetry also can. Here you can see that they have a lot of ions. Okay, there is no ions in the product, so it means there is going to be a decrease in electrical conductivity. you can also do that. Yeah, so many things that you can do, okay, so that you can monitor the progress. Yeah, but make sure, okay, based on whatever method that you choose, you can identify whether they are continuous or sampling. In this case, if it is electrical conductivity, automatically this is going to be continuous. Okay, so all this, okay, you need to know. Yeah, now once you use the methods, okay, once you use the method, you have identified, okay, and so on, okay, you are going to actually get a data. Yeah, so you can find out the concentration. Yeah, sorry, you can find out the concentration. Okay, and you can actually get the time, okay, because you're monitoring according to the time. And let's say this is going to be an equation, cyclopropane, okay, changing into propene, and cyclopropane is going to be the reactant and propene over there. You can just roughly see, okay, the concentration of cyclopropane is decreasing. Yeah, concentration of propene is increasing because it's generally product. Yeah, even this one also, okay, there is a video that I've made about graphical rate of calculation. I will go fast over here, but if you want to go slow, yeah, you can go through the video, yeah, that I've given over here. Now here, okay, I just plot, yeah, they according to textbook, okay, what they did using the table, they just will plot the data for propene. Do remember, propene is going to be the product. So it means we are expecting the concentration to be increased. Using this data on the table, okay, we can only analyze, okay, in the graph form. So in graphical form, we will plot the data, concentration against time. So if you draw the concentration of propene against time, you can see a curve over there. You can see starting from 0, okay, all the way to 40. You can see the rate. Okay, what can you say about the rate of the reaction? Okay, rate, okay, do remember the rate is defined by change in concentration divided by time. Okay, and by this time around, you should know how to measure rate. Yeah, if you want to measure the rate at point, let's say for example at point 30, okay, this one. Okay, how do I measure? Okay, straight away you need to draw a tangent. Okay, I just draw a line over here. I draw a tangent. Okay, make sure it touches at that point only. Yeah, and what I need to do next, okay, I need to actually find out the gradient. How do I find out the gradient? Yeah, I need to draw the triangle. Okay, and then, okay, you find out what is this and divide by this. Okay, so it's going to be, what is that? Okay, this part is going to be concentration of propene divided by what is this? This is going to be time. In this case, it's minute. Later, you need to change it into seconds. Yeah, so when you are going to get the gradient, yeah, the gradient is automatically the rate. Okay, it's automatically the rate. Now, if I erase this part, okay, I just want you guys to think about what happens to the rate, yeah, as the time progresses. You can see that if I draw a triangle over here, okay, you can see that the gradient is more, and the gradient is, as the reaction progresses, the gradient become less steep. Okay, so it means that, okay, your rate of reaction, the gradient is going down. So the rate also goes down. Yeah, the rate goes down until, okay, until the reaction sometimes, okay, once the reactant is fully used up, okay, the reaction will actually go like this. Okay, where the concentration of propene will become constant. Why constant? One of the reactant is completely used up, yeah, or the reaction has been completed. So what we can say about the rate when it becomes a constant line like that, the rate, okay, therefore the rate at that time is going to be 0. Okay, do remember. So it means that the rate is going to be decreasing. Okay, it's decreasing. Now, if you look at the next graph over here, okay, this graph in chemistry, what we do is there's so many rates at different times. Okay, but we are interested with initial rate. Now, what is initial rate? So if you look at 0 to 5 here, what they did was, okay, they enlarged this portion of the graph. Okay, they enlarge this portion of the graph, and you can see if I make it bigger, okay, the graph looks like a straight line, okay, in the beginning. So if I just put it over here, you see it's a straight line. Okay, so do remember, this is going to be your original graph, the A. Okay, this is the from eventually they are going to become a curve. Yeah. Now, if you want to find the rate at point zero, yeah, point zero time, yeah, that is going to be what we call as initial rate. And it's going to be slightly different, okay, than how we draw the tangent, because tangent over here is quite easy to draw. Okay, you just need to make sure that they touch at one point, okay, and then you balance the line, okay, and then you can come up with a gradient. Yeah, you can calculate the gradient. But here maybe it's going to be slightly complicated. How come I can draw the line, just one line, and suddenly that become tangent? Yeah, this one, okay, you can have many lines. Okay, if I put like this, what is the difference of this line and this line, you may ask me. Yeah, the idea is tangent, it will pass through that point only. Yeah, touches that point only. If I draw using the blue line that I just simply draw, what happens if I extend? There is going to be some sort of intercept. Yeah, so if I extend the red line, you will see some sort of intercept. Yeah, but if you follow, okay, if I erase this blue line now, okay, if you follow the black line that they have drawn, it's just touching that point, and it looks as though, okay, that line, if you continue, okay, the black line and the red line is going to be like a straight line. Yeah, they join, merge together. Okay, so you need to draw, okay, you need to come up with a line, okay, which is the line B, okay, to help to calculate about initial rate of reaction. This is going to be the difference. Yeah, now if I move on, okay, if let's say same thing, okay, earlier we draw the product. Okay, let's say now, okay, the same situation, but now we look at the concentration of reactant, cyclopropane. The information is given over there. If I represent them in a graph, quickly you can get this graph. They started at 0.0, 1.5. You can see 0.0, 1.5. Okay, and you are getting, yeah, you are getting a curve. Okay, and you like what you are expecting. Okay, the concentration is decreasing. Yeah, do remember, this is why I leave it over here. Do remember, when you are looking at concentration, okay, versus time, okay, concentration versus time, there are going to be two types of graph that we can expect. Okay, one is going to be a graph that goes like this. Okay, another one is going to be a curve. Do remember, this one I'm talking based on product, okay, because it's decreasing. Yeah, so sorry, based on reactant, because it's decreasing. Yeah, concentration is decreasing. So here, okay, in this case, later I'll come back to that. Okay, but you can see here we are going to have a curve. Okay, we are going to have curve, and the same way that we use for the gradient. Yeah, gradient, you see concentration and then the time. Okay, gradient will tell us about, okay, your rate of reaction. Okay, if you draw like in this case at time 10 minutes, okay, they ask you to calculate the slope, okay, or the gradient. Okay, they have calculated. Okay, you can see a tangent line is given over there, and they have calculated and give you this. Okay, do remember this is negative because gradient going to the left. Yeah, the line is going to the left, is going to be negative, and you can see that is going to be your gradient, which is going to be your rate. Yeah, rate for reactant. Yeah, so you can calculate many ways. Okay, you can see so many ways that you can calculate, where you can use different lines. And if you look at this line, this particular line, it is going to start at point time equals to 0. So this is going to be what we call as initial rate. Okay, initial rate. How to calculate and so on. Yeah, you can look at the way they have calculated over here. Okay, basically is to find the gradient. Yeah, to find the gradient, and it's all written over here. Okay, in this case, this one I'll skip first. Okay, I don't want you to get confused now. Okay, but you can represent, or you can get the rate of reaction from the graph. Okay, in summary, what we did, okay, first, okay, methods of tracking the progress of the reaction. Okay, we have sampling, we have continuous. After you do the method, yeah, you do the analysis and so on, then you are going to put everything in graphical form. Okay, once you put everything in graphical form, you are going to do calculation. Okay, calculation of what? You are going to calculate the rate. Yeah, so all these are going to happen. Okay, it's going to happen. And why we do this? Yeah, why we do this? Okay, because from the graph we can get a lot of information. Yeah, and the reason why we do this, okay, is basically we want to get rate equation. Yeah, rate equation. So what is rate equation? Okay, if you look at cyclopropane, okay, to become propene, do remember rate equation. Okay, those of you you would have actually done equilibrium and so on. Okay, it's going to be slightly different. Okay, because we are only going to use reactants. Okay, and in this case, the only reactant is cyclopropane. I will come into detail to that later. Yeah, but the reactant over here is cyclopropane. Okay, generally, okay, the rate of reaction is K. Okay, what is K? K is going to be rate constant. Yeah, rate constant. You can see here. And this reaction here, concentration of cyclopropane over there. Okay, this rate, yeah, this rate of the reaction, okay, or the rate equation can be only determined through experiments. You cannot determine them, okay, using stoichiometric equation. Okay, what I mean cannot determine from stoichiometric equation, you can have a look over here, because some of you will be thinking, yeah, this is going to be reactants, yeah, reactant H2, I2 is also reactant, everything in front is one, or that's for this one, bracket like this, H2 and I2, 1 and 1, K. Okay, maybe because of that. Okay, the answer is not, okay, it's not because of that. Okay, it's not because of that. It just happened to be, it is going to be correct. Okay, but if you look at the next stoichiometric equation, you see the reactant, this is reactant. Okay, three reactants, but you can see in the rate equation, CO and O2 is missing. Okay, they are missing. Okay, this one, okay, we will discuss later. Yeah, they are missing. So it's not dependent on the stoichiometric equation. And here, one, why suddenly become two? This is all based on experimental values. You can see here hydrogen and NO. Okay, hydrogen and NO are there. Okay, but two, this is one. Okay, NO2. Okay, so it's not fixed. Okay, it's not fixed. So please remember this. Okay, it is based on the experimental value. Yeah, so if you go here, okay, since I mentioned about experimental value, some of the details are given here, so maybe this one will help us to write the rate equation. For example, you see there is going to be this. Okay, they say the rate. Okay, if I want to write the rate equation, rate is proportional to the concentration of C12H22O11. Proportional. So you just put K. Proportional, you just put, okay, this C12H22O11 1. Okay, this one you just put 1. Okay, why proportional? Okay, why proportional? This one is going to be something related to your maths. Okay, y equals to mx plus c. Yeah, so if it's going to be, let's say, if I write down y equals to, let's say, k, I change the m into k, rate constant k, and then I just put x to the power of 1. Okay, or simplify y equals to 2x. How do I draw y equals to 2x? Okay, you can draw y equals to 2x by a straight line graph like this. Okay, that is what we call y is proportional to x. Okay, that's why it's proportional. Okay, so this is going to be proportional to the power of 1. Proportional to the concentration of H plus. You put here and then proportional. Okay, so here no need to put 1. You can see they just put, okay, just bracket is enough. It's understood. It's 1. This is done. Okay, if you look at the next example, you see here rate is proportional to concentration of HgCl2. So just proportional to the power of 1 and proportional to square. This one you need to put C2O4. This is square. You put 2. Okay. What does it mean? Yeah, basically if you have y equals to x to the power of 2. Yeah. So if I draw this graph, this is going to be a quadratic graph. Okay, it's a quadratic graph. But if I want to change this graph into y, then I put x squared. Okay, those who are actually very good in maths, you should know that they will give you a straight line. That's why y is directly proportional to the square. Yeah, so basically it's all maths. Okay, it's all maths. So if you look over here, the third one, okay, they say it's proportional to concentration of this. So you just put rate equals to k. I forgot the k here. K, then you put the proportional CH3CO CH3 to the power of 1, and proportional to the concentration of H plus. You put H plus to the power of 1, and it has no effect. No effect. Okay, you put the I2 0. Okay, you put the I2 0. Okay, why I2 0? Anything 2 to the power of 0 is 1. 3 to the power of 0 is 1. Anything to the power of 0 is 1. Okay, that's why, okay, if you put over there 0, okay, it means that this is going to be actually 1. Okay, so you only write this one, okay, which is this. Okay, I hope you understand this. Yeah, but if you don't understand, yes, okay, we will move on, and then there is more explanation that will follow. Okay, so it means now I have introduced to you what we call as order of reaction. Yeah, what is order of reaction? Okay, according to the textbook, is the with respect to particular reactant is the power to which the concentration of the reactant is raised in the rate equation. Yeah, like for example, okay, if you have this rate equation, okay, do remember this is rate constant. Okay, you can see this one didn't write anything, it means 1. Okay, what does it mean? Okay, it is going to be first order. Okay, first order with respect to, okay, with respect to concentration of H2. Okay, that's the meaning. Okay, that's the meaning. You can see it's all written over there. And then for here, these two, it means that second order with respect to NO. And we also have learned just now, right? The proportional. It means to the power of 1 is proportional, straight line. And this one, second order, is going to be like quadratic. Okay, quadratic is going to be proportional to the power of 2, squared. Yeah, it's proportional to the square. And the only thing extra we need to learn is going to be what we call as overall order. Overall order is quite simple. Okay, you just need to add the order. If this is 1, this is 2, so 1 plus 2 equals to 3. Okay, they will ask you what is the overall order, just like that only. Yeah, and they won't ask you more than that. Okay, so you need to identify whether it's first order, second order, or zero order based on the experimental data. Let's actually move on. Okay, units of K. Okay, what is K? Rate constant. Okay, so you can calculate the units of K. Yeah, let's say for example, I have written here for equation number 3. So maybe I'll just do for you for equation number 1. Yeah, you see rate. Okay, is written rate equals to K concentration of H2 and then concentration of I2. Okay, so that is going to be the rate. So we know, okay, if you want to find the K is going to be rate divided by concentration of H2, concentration of I2. What is rate? Okay, rate is going to be change in concentration divided by time. So the unit is going to be mole per dm cube per second. And this is going to be concentration to the power of 2. So it's going to be mole per dm cube. Okay, and then we have another mole per dm cube. So you can just, okay, cancel this part, and the unit is going to be, you bring this mole, okay, bring up -1, bring up, okay, it's going to be opposite, yeah, negative 3 will become 3, and then per second. So this is going to be how do we find the unit, okay, for rate constant. Yeah, the same thing can be applied. Okay, you can just go through for equation number 3. Yeah, this one, and they have calculated, and you can calculate the units of K. Okay, even if you want to do more, okay, you want to follow up on the units of K, there is going to be 4 examples over here with the working for you. Yeah, to go through. Quite easy. Yeah, quite easy. The only thing that you need to remember over here is going to be your rate. Okay, is always going to be mole per dm cube per second. Yeah, remember the definition, the first slide that we did. Yeah, the definition is going to be change in concentration divided by time. Yeah, so that using that, okay, you can calculate concentration. Yes, generally concentration is mole per dm cube. Yeah, and then you can calculate on your own. Yeah, this is going to be checkpoint 3. And now, okay, we go into the graphs. Okay, the graph, okay, I put all the graph together. Okay, no need to do one by one. Okay, basically we have main we have two graphs. Okay, earlier we did, okay, if you what I mean by two graph, earlier we did concentration versus time. Okay, concentration versus time, and I mentioned that there are two types of graph for the concentration versus time. One is going to be a straight line going down, another one is going to be a curve. Yeah, so we leave the concentration against time first. Okay, we go to another graph, which is going to be the main important graph over here, which is going to be when you have rate equals to K and then you have concentration something. Okay, generally, yeah, we are dealing with something y equals to mx. Yeah, if it is going to be, this is going to be y-axis, this is going to be your x-axis. Yeah, so something like that. Yeah, if you follow maths. Okay, so if I have, let's say for example, okay, if you have zero order reaction, okay, if you have zero order reaction, for example, okay, I give you one example because we don't see it from the equation itself. It must be from the experimental data, and they found out, okay, for this reaction, this is going to be a zero order reaction, and they say rate equals to this. Yeah, so what does it mean? Yeah, what does it mean if I use y equals to k and this is x to the power of 0? Yeah, so it means that this is going to be y k, this is 1. Anything to the power of 0 is 1. So it means it's going to be y equals to k. Okay, how do we draw y equals to k graph? Yeah, so this is y, this is going to be x, y equals to k. This is going to be the graph. Okay, so if I just put this is going to be zero order. Okay, so it's going to be a constant, yeah, which is going to be zero order. So do remember what type of graph that we are drawing. We are drawing rate against concentration. Okay, rate against concentration. The best way to remember this is rate equation. Remember rate equation. Rate is going to be K and then times the concentration. So it means you just need to use y equals to mx, the graph. Yeah, so it's much more easier to remember that way. Zero order, one line straight. Yeah, constant line. Yeah, and then you have the first order. Okay, this is one example, experimental value they found out. This is going to be first order with respect to N2O. Yeah, so you will have this. Okay, if I want to represent this in a graph, okay, it will become y equals to k x to the power of 1, x to the power of 1. So which is similar, maybe y equals to 2x. How do we draw y equals to 2x? Y equals to 3x. How do we draw? It's going to be this straight line, okay, that passes through 0. Okay, so this is going to be our first order reaction. Okay, quite simple. Okay, and then the last one, okay, for the second order. Okay, this is going to be example of second order. Do remember, okay, according to the experiment data, not all the reactants will be selected, and they found out, yeah, only this one, okay, the reactant will be involved, okay, and then it's going to be second order. So what does it mean? It's y equals to k x to the power of 2. So it means like something y equals to 3x2. How do I draw this kind of graph? Yeah, if you know maths, yeah, it's a quadratic graph. Yeah, so this is going to be a quadratic graph. It's a second order reaction. Yeah, so all this, okay, if I put it together, okay, you can see the graph itself. Zero order, second order, first order. Okay, you need to know the shape. Okay, no need to memorize. The moment you know the rate equation, you should know zero order. Okay, you know the rate. Okay, the rate is independent of the concentration. It doesn't, the concentration don't affect the rate. So it's going to be independent. And then you see the first order just now. Okay, the first order we know is directly proportional. That's directly proportional. And you see the second order is going to be directly proportional to square. Okay, so it means it's a quadratic graph. Yeah, you need to know with all this graph. You get familiar with this graph. Now, Okay, if we revisit again the concentration versus time, the earlier, the one that we did earlier. And I mentioned to you there are two types of graph for concentration versus time. One is going to be a straight line going down like this. Okay, this one we are talking about reactant, reactant. Concentration of reactant is decreasing. And you can see there is going to be another graph, which is going to be a curve. But to be exact, there are going to be two types of curve. Two types of curve. Now, when you look at this graph, when we draw the graph and so on, automatically when you have a straight line, that belongs to zero order. Please remember that. Why? Okay, because you see concentration against time. If I find out the gradient here is the same as the gradient here, the same as gradient over here. So the gradient, what is the gradient? The gradient is going to be constant. If the gradient is constant, okay, we already know the gradient is going to be constant. Okay, so in this case, it's going to be zero order. Okay, why? Because this is going to be like the graph that we learned earlier. Zero order. The rate, the rate is k. Okay, the rate is going to be k. So here, okay, if you look at this, okay, the moment it's going down, the constant rate, it's going to be zero order. Okay, we have first order and second order. It's going to be difficult to see, but if you have first order and second order together as a graph, easier to see. Why? The moment the curve, okay, is going to be more steeper, okay, if it is more steeper, that is going to be a second order. Okay, and then they will intersect over here. So you can see, okay, first and second order, the graph is going to be curved, and then the curve for the second order is deeper, and then the curve of the second order, longer tail. Okay, whatever it is, okay, if they exist together, easier to identify. But most of the time, they don't exist together. When you draw the graph, okay, when you sketch the graph, you only sketch one. It's either you see a straight line or you see a curve. So how do I identify first order and second order? Zero order, quite easy. Okay, it's a straight line, straight line going down. Okay, but first order and second order to identify, you need to look at what we call as half-life. You need to look at something what we call as half-life, which is going to be the time taken for the concentration to become half of the original value. You see, this is the concentration. If the initial value is 4, okay, to become half is 2. Okay, you can see it takes this amount of time, which is 17 seconds. Okay, and then from 2 to become half of it is going to be 1. You plot the graph and then you get this. You can see 17.3 and then so on. You can see roughly they have represented this in a table. If your half-life, okay, is constant or almost similar to each other, 17, 17.3, 16.7, it's almost to 17. If it is constant, okay, it means that this is going to be a first order reaction. First order reaction. So coming back over here, how do I know which one belongs to first order? Okay, you go and find out the half-life. Half of it, you go and find out. Okay, and then take another half, you go and find out. If it is going to be same constant, okay, then it's going to be first order. If it is different, then it's going to be second order. We will revisit this later in the other slides here. But in summary, in summary of the graphs, okay, what can I tell? There are two types of graphs. So I will just draw over here. Okay, there are two types of graphs. One is going to be the rate based on the rate equation. Okay, rate equals to K and then the concentration. So the rate, okay, it's going to be rate versus concentration. So if it is going to be zero order, okay, zero order, then it's going to be rate equals to K only. How do I draw rate equals to K? This straight line, just like this. Okay, this is going to be for zero order. And how do I draw, okay, the rate, okay, for the first order, K and then 1, okay? So it's going to be something similar to rate equals to Kx. How do I draw Kx? Just like this, okay? This is going to be first order. And how do I draw, okay, the rate, okay, equals to K and then concentration to the power of, okay, concentration to the power of 2. So it's going to be similar as rate equals to kx to the power of 2, which is going to be proportional to the square, which is going to be a curve. Okay, and this is going to be your second order. Okay, quite simple. Yeah, if you look at it. Okay, but there is another one that I just mentioned to you. Okay, there is another graph. Okay, which we started that also. Yeah, so now we revisit is concentration. Okay, concentration versus time. Okay, versus time. So this concentration versus time, there are two types of graph. Yeah, one is going to be, let's say now we are talking about reactant. Yeah, so there are two types. Okay, one is going to be the concentration decreases over time. The moment you see this graph, this is automatically zero order. Okay, zero order. Okay, it's going to be a constant rate. Yeah, and then okay, there is going to be another two more graphs. Okay, which is going to be curves. Okay, so one curve will be steeper. Another curve is going to be just like this. Okay. So the one that is steeper, okay, is going to be second order. The one that is going to be less steep is first order. But okay, we cannot identify directly. So what we need to do, okay, we need to go and look for half-life. If the half-life, okay, is going to be constant, then we can confirm that it's going to be a first order reaction. Yeah. So that is going to be the summary of the graph. If let's say you still couldn't understand, yeah, please go through this video. Yeah, I went through in detail over that. Yeah, you can watch it again and again until you guys understand. But if let's say this drawing is too, I know it's messy. Yeah, this is going to be the actual thing that you should know. Yeah, so the two graphs that you need to do to know is going to be these two graphs: reaction rate, yeah, rate versus concentration, and concentration versus time. And I went and introduced to you the half-life. So do remember, half-life, it's important when it comes to first order reaction. Okay, first order reaction, half-life is going to be constant. You need to know what is the definition. Yeah, so the definition is over there. You need to remember. Yeah, you need to know how to calculate. Yeah, please go through that as well. Okay, and you see here in your textbook, they have given you the half-life for zero order. They have given you the half-life for second order. You can see the half-life is decreasing here, half-life is increasing, but I have actually blurred that a bit. Okay, because in your syllabus, what is important? Only for first order, you need to know for the half-life. Okay, and even the equation. Okay, later you are going to be given a formula. Okay, to calculate something that is only applicable when they are going to be first order reaction. So do remember that. Extra video, yeah, it's there. Yeah, if you find this one is too fast, okay, please go through those videos. Yeah, the checkpoint 4, yeah, of course we don't have time to go through this, but if you have time, yeah, if you have the graph paper and so on, you can actually complete this checkpoint 4. You see how to methods of monitoring the progress. Okay, plotting the graph. When you plot the graph, it's smooth downward curve. So it means what? This is concentration and time. Okay, concentration against time, smooth downward curve. Okay, it means curve. It can be first order or second order. Definitely not going to be zero order. You have already learned this. And what you need to do, yeah, they ask you to find two successive half-life. You calculate the half-life and you find out the half-life is like this, and then more or less the same. So they concluded, okay, that this is going to be a first order reaction. But if you want to see more yourself, yeah, the best method is to plot the graph yourself. Yeah, you can try on your own. Yeah, now the last part that I want you guys to know is going to be the calculating the K from half-life. Yeah, you can use this formula. Okay, half-life is going to be 0.693 divided by K. Yeah, K is rate constant, and this is going to be applicable only for the first order reaction. Okay, so let's say, for example, you see this is first order, this is going to be first order. Yeah, you can just use, okay, use the formula. Okay, apply the formula. You can calculate what is K, or you can calculate what is going to be the half-life. Okay, I don't want to go in detail. This is straightforward only. The only thing you need to remember over here is the formula. Use the formula, memorize, and then apply. Quite simple. Yeah, quite simple. Now, the one that I want to go through with you guys is going to be this example, but if this one we couldn't do everything also, no worries. Yeah, this one I have a video on this as well. Okay, you can just go through the video. There are 3 videos here, past year paper discussions. Okay, but here what I want to show you over here is going to be if you have the reactants. Okay, you see the reactants, all these are going to be the experimental data, and you want to find out, okay, to determine the order with respect to each reactant. So how do we do that? This is how do we apply the skill. Yeah, apply the skill. So in order to apply the skill, you see, if it is going to be, my question is like, for example, if the concentration from experiment 1 to 2, yeah, you can choose any of the data, but you see, if it is experiment 1 to 2, this one become double. Okay, when I times by 2. Okay, but I just want to focus only, okay, what will happen to my initial rate. Okay, what will happen to my initial rate when I change the concentration of O2 only. Yeah, if it is like that, you need to make sure that these two are constant. So when you select, when you select the data, it means that you need to select the data. One of it must be constant. You have to do it one by one. Yeah. So if you put times by 2, if you look at this data, what happened to the initial rate, you can see the data is also going to be times 2. What does it mean? Yeah, it is going to be, if you times by 2, initial rate also times by 2. This is what we call a proportional. You times by 3, it is also going to be times by 3. It's proportional. With respect to what? With respect to O2. It means this is going to be first order reaction. Okay, first order reaction with respect to O2. I'm not done yet. Yeah, I'm not done yet. So rate equals to K. I'm not done yet. I need to find out with respect to NO using the experimental data. So what I need to do, I erase this and I need to select, okay, another set of data, okay, where the O2 is going to be constant. You can see the O2 is constant. Okay, I can select this experiment 2 and 3. Why? If I times by 2, okay, 0.032 to become 0.064 times by 2, what will happen to my data over here? Okay, and if you do that, if you calculate, this is basically, okay, 3.28 times 10 negative 2 divided by 8.15 times 10 negative 3. This is going to be, you will get times by 4. Okay, you will get times by 4. So this is times by 4. What does it mean? Times by 4 means it's simply 2 times 2 to the power of 2. Okay, 2 to the power of 2. So this one, you see, is directly proportional to the square. Okay, you times by 2, it is going to be times by 4. You times by 3, then you need to times by 3 to the power of 2, which is going to be times by 9. Yeah. So now you confirm that with respect to NO is going to be to the power of 2. This is going to be your rate equation. Yeah, don't worry if you feel this is too much already. Yeah, again, your teachers will help you. Yeah, and if you want to go through the there is a worksheet also here. I have all the worksheet also. You can download the worksheet and you can try on your own. You can listen to you can watch that video. Yeah, the same thing. Okay, this paper, I think one of the paper is there. Okay, you can just go through that. But okay, in the end, you are going to get this rate, okay, equation. And okay, they ask you to calculate the initial rate in experiment 4. So what you need to do, initial rate, experiment 4. So now, once you know how it applies, okay, you can see from here, 1 to 4. Okay, this is going to be times by 3. Okay, times by 3. And then here, this is going to be times by 3. So what will happen over here? Yeah. So you see, for NO is going to be square. Okay, so it means this one must be 3 to the power of 2. Okay, 3 to the power of 2. And for this one, you combine. Yeah, you combine. This is going to be first order for O2. Yeah, so it means times 3. So what you need to times together? 9, okay, times 3, 27. So you need to have 27 times 4.08 times 10 negative 3. and you will get the answer 0.11. Yeah, so this one you can try on your own. Yeah, you can only do that, okay, once you know the rate equation, and then write the rate equation. Yeah, you write that same rate equation, and you can calculate the units of K. You can calculate the rate constant. Just use the experiment number 1, put all the values there. You can calculate what is K. Okay, and this one you will get 332. Go and try yourself. Yeah, you try yourself. So that is going to be the lesson for today. Yeah, extra stuff is all here. Okay, there are so many links of the video that you can go through. Okay, and then please complete my Padlet. But